All right, folks, good evening. I'm here today to talk to you about the second derivative and something called concavity. Now, as a review, remember that the derivative's purpose is to show the instantaneous rate of change. Let me get a pen out here. It shows the instantaneous rate of change of a function's y values at a given value for x, right? So it tells me if my y values are getting bigger or smaller, right, if the function is increasing or decreasing at a particular value for x. So we know that y prime talks about the change in y's at a given value for x. So what would happen if I took the derivative of the derivative? Well, since the derivative is slopes, shouldn't the derivative of the derivative be how my slopes are changing? Does that make sense, guys? All right. So we can say that the second derivative's purpose is to tell me how the first derivative is changing, right? So the second derivative's purpose is to show the rate of change of a function's slopes at a given value for x. Okay? Now, if you think about that, what we're saying is the second derivative tells me if my slopes are getting bigger or smaller as I go along my graph. Now, here are some definitions for us. Concavity. We have two types of concavity. We have something called concave up and we have something called concave down. Now, if you think about the word concave, concave means like that or like that, correct? You can either concave down or concave up. Now, the definition of concavity for concave up and concave down is as follows. An interval is concave up if and only if the slopes or the derivative are increasing over the interval. An interval will be concave down if the slopes, or f prime, are decreasing over the interval. Okay? Now, let's go down to this graph that I have right here. Looking at this graph of this green function here, let's take a look at the regions. Now, I told you that concave down means that it's opening downward. So this region right here is concave down. But why is it concave down? According to the slope. Well, let's take a look. If I were to draw little tangent lines in here, the slopes of those tangent lines would be the slope of the point of the graph at those points, correct? Well, look what's happening to these slopes. Would you agree that my slope here might be like 9? Here my slope would be like, well, it doesn't seem as steep, so it may be like 8. Here the slope would be equal to like 7. Here the slope would be, say, 4. Here the slope would be like maybe 1. Here the slope is a half. We know that at a relative max the slope has to be 0. Coming down, the slope would be negative a half. Here the slope might be negative 2, and so on, correct? So as you can see, over this concave part of the graph, aren't my slopes getting smaller and smaller and smaller? Whereas in the next region, if I look at those, in this region right here, this is definitely concave up, opening upward, right? According to my definition, a concave up region occurs when the slopes are increasing. So that means that if I drew my tangent lines in here, my tangent line here would be a slope that's negative, but maybe it's like negative 3/2. Here, that tangent line slope will be still negative, but not as steep. So it would be like -1. Here, that tangent line slope would be like -1/2. Here, again, my slope will be 0 at that relative minimum. And here, my slope is increasing to, say, 1/2 for that tangent line, and so on, correct? As you can see, as I move along a concave up region, the slopes are increasing. So, by definition, intervals that are concave up is where my derivative or my slopes of my function are increasing. Now remember, it's the slopes that are increasing, not the y values. Okay? So, putting that together, if we take a look at the red part of the graph and the blue part of the graph, if I go from the slopes decreasing in the red to increasing in the blue, at some point it has to change. There has to be a place where you stop decreasing, you start increasing. This point right here is called a point of inflection, where the graph changes from decreasing slopes to increasing slopes or vice versa. That is called a point of inflection, and that definition is right here. A point of inflection is the point on the graph where a function changes its concavity. Okay? Now, points of inflection will be to the first derivative when we use the second derivative, right? Points of inflection will be like the critical values of the first derivative function, right? Just as the critical values for a regular function can be found using the first derivative, points of inflection will be found for the derivative using the second derivative. Okay? And that's what I've said right here. The points of inflections, what I call PIs, are the critical values of the derivative function. Therefore, we will be treating them in the same way in comparing the derivative function and the second derivative function. Okay? Okay. Now the next thing, we're talking about these tangent lines. Now let's talk about some rules that we need to know. When I was drawing the tangent lines for a concave down region, notice to draw these tangent lines, the tangent lines will always be above the curve if I'm in a concave down area or interval. For a concave up, the tangent lines will always be below the curve. That is a very popular idea that AP likes to ask about if the tangent line is above or below the curve, and we'll talk more about an application of that later on this year. Alright, so that's a rule that we need to know about these tangent lines that we're drawing and the concavity, whether it be concave up or concave down. Okay, the next thing, so how do I find the intervals for my concavity, and how do I find my points of inflection? Well, that's this next idea right here. Finding concavity using the second derivative. The steps to do that are very similar to what we do to find critical values and relative mins and maxes. What we'll do is we're going to find the discontinuities in the domain of the function just like we always have. But when we do this, we're going to go straight to the second derivative, and we're still going to set the second derivative equal to 0 and undefined just like we did with the first derivative. Now, after you've done that, you need to place those answers on a number line for the second derivative, just like we did in the first derivative, and then plug in test points into that second derivative, to determine the concavity. Okay? Now, if you look at this function I gave you, to find this guy's concavity and points of inflection, the first thing we do is we state the domain, and the domain, since there's no red flags, is negative infinity, positive infinity. Now I go to take the first derivative of this guy, which would be 3x squared minus 8x plus 4, and I'm going to keep on trucking and go all the way into the second derivative, which would be just 6x minus 8. Now, if I set this second derivative equal to 0, I get 6x minus 8 equals 0, so x would equal 4 over 3. From here I take that value, I put it on a number line for the second derivative, This is the only possible point of inflection. Now, just like with relative max and mins, for this to be a point of inflection, I need to change from concave up to concave down or vice versa. So I better see a sign change in my second derivative around the 4/3. So now I'm going to pick a number to the left of 4/3. So 0 is a nice number to pick. If I plug 0 into this second derivative, the second derivative at 0 would be -8. So I know to the left of of 4/3, my second derivative is negative. So that tells me I'm concave down, and I always abbreviate it to be CD. So this interval from -infinity to 4/3 is concave down. Now, if I test a number to the right of 4/3, say 1,000,000 into here, f double prime at 1,000,000, well, wouldn't that just give me a positive value? And that's all I care about. So I know to the right of 4/3, the second derivative must be positive. So that must be concave up in that interval from 4/3 to infinity. And therefore, I can say that 4/3, or x equals 4/3, a PI occurs. Now, if you actually want the point of inflection, you'd have to plug that x equals 4/3 into the original function to find the y value for that point of inflection. Okay? And then the last idea, ladies and gentlemen, is this important idea. Just like when we were talking about the first derivative, the reason why we need to know that domain, the domain restrictions, even though your graph can't exist at those domain restrictions, concavity can change around those discontinuities. So on vertical asymptotes, you have to put a vertical asymptote on your number line for, or your sign chart for f double prime. You would also have to put, like if it was a piecewise function and you had some type of discontinuity there, you would have to test that one for, like if it was a jump discontinuity, you'd have to place that value on your number line as well to test around that, because you could change your concavity around that as well. Alright guys, well that's it, and I'll see you in class.